Good morning, everybody. I hope you've all been doing well. Our new work chapter begins with a problem involving a cow trying to leave this barn. The goal is to figure out how much work we do on the cow when we apply this varying force on it. Since we haven't talked about the concept of work yet, let's take just a moment to go over the definition. The amount of work done in the process of applying a force on an object from some initial point, which I'm calling 1, to a final point, 2, that is the dot product of the force vector F and the displacement vector S, with a constant force involved. If you haven't been introduced to dot products of vectors yet, or perhaps in case you forgot, here's a real quick reminder. Let's say that I have two vectors in a two-dimensional space, so like an xy plane. Let's call those two vectors A and B. If I want to take the dot product of these two vectors, we'll simply break each vector down into components, multiply like components together between the two of them, so x with x and y with y, and then sum everything together. And the final result will be a number, or to be more specific, a scalar. So something to keep in mind. We don't have a constant force in this problem, however, so we'll have to generalize this definition to one that applies to varying forces. It's a pretty similar definition, but now there's an integral involved, and we've switched out the displacement vector S for an infinitesimal displacement vector ds. Let's try to understand what that change means in the context of our picture. I've said a few times now that our problem has this varying force going on. And if we draw the force vector, at first it's just 20 newtons pointing to the left, right at the barn door. But as the cow continues to resist and moves further to the right, we have to apply a greater and greater force in the negative direction in order to push it all the way back to the barn door and get it inside. For ds, we're going to break up the displacement from 0 to 6.90 meters into a series of infinitely small displacements, of which I'll show a couple here, like this. The reason that we're doing that is because as the displacement changes, so too does the force, because of the factor of x in the x component of the force vector, which I've circled here. Instead of doing a ridiculous number of dot products to account for each tiny change in displacement as we move to the right, and then having to add all of those results up, we can just use an integral, and it does most of the work for us. There's a couple things that we can simplify here, though, since everything occurs entirely in the x direction. We don't really need to carry around this entire force vector, since the y component is just 0 everywhere. So let's go ahead and chop that portion off and just keep the x component that we were given from the problem description. The same thing can be replaced down here in our picture of the force vector below. Let's also switch out ds, which accounts for movement in multiple directions, for just plain dx, since all the movement is in the x direction. With all that taken care of, let's go back to our integral definition and get started on calculating the work done on this cow. We'll switch out the force and infinitesimal displacement vectors like we did in the last slide for f sub x and dx. This eliminates the need for the dot product, so we don't have to worry about working with vectors anymore. If we insert the expression for f sub x and factor the negative out front, the integration is pretty simple, and it results in the following expression. We only need to evaluate at the top endpoint here, since the other one causes all the terms to just go to 0. So why write that out and do the work if we don't have to? If we multiply and collect like terms and truncate our result down to 3 significant figures to match what we had in the problem description, here's what we get. Before we finish, let's ask ourselves, why is it negative? Well, that's because the force and the displacement vectors are acting in opposite directions. So the work that we do on the cow is negative as a result of that. And that's it. We're done. Thanks for watching, everyone.